what I want to talk today mainly is about heat transport, and particularly anomalous heat transport in systems, in some one-dimensional systems. These systems, as Bernard mentioned, they are different from diffusive systems. They have some means of transport which are faster than diffusive, and as a result, they produce anomalous heat transport that I want to discuss. So I want to give a very brief overview of roughly what is known and not known in this field, and then enter into some models that we have studied and see what we can find there. And the works I'm going to describe are done in collaboration with Julian Sevidini, Anupam Kundu, Asaf Miron. Julian and Anupam are postdocs at Weizmann Institute. Anupam has left already, and Asaf is a master's student. And then there is another work, I may get to it towards the end. Ori Hirschberg is a former student of mine. Okay, heat transport. Typically, you have a configuration in this context, a system, where you put two heat reservoirs at temperature T plus and T minus, and you ask what is the energy current that flows through the system. And usually what one finds is the usual Fourier law, where the current is proportional to delta T over N. N is the length of the system, and delta T is the temperature difference. And this is for diffusive systems. In diffusive systems, the energy, of course, is conserved. There is the EdT is minus the current, and the current is proportional to the temperature gradient. And as a result, you get a linear profile of temperature and a current which goes like delta T over N. That's the usual picture that one gets. It turns out that in many one-dimensional systems and in some two-dimensional, some anomalous heat transport was observed. And the main observations are the following. First of all, the current doesn't go like delta T over N, length of the system, but it goes with the slower power law of N. So, which means that it's much higher than one would expect in diffusive systems. Okay. In addition, if you look at long range, the time correlations of the total current, you look at the current and you sum over all instantaneously integrate over the system size, and you look at the current, the instantaneous total current correlation function. One observes that it decays rather slowly in these systems. It decays like T to the power, some negative power, with power which is smaller than 1, which means, so that's another observation that go together with the fact that, that the current decays slowly with the system size. These two things are very intimately connected to each other. The third property that one usually sees, there is a rather non-trivial temperature profile. Namely, if you look at the temperature profile of the system, it looks something like that, where at the boundaries, in the connection to the heat reservoirs, you have some singularity of the temperature profile. That is, dt dx goes like x to the minus, say, some power, nu, close to the x equal to 0, and similarly on the other end. So there is a singularity of the temperature profile at the end. And the point is that this happens no matter how small the temperature difference is, which is rather surprising. That is, you can make the temperature difference between the two sides as small as you want. Nevertheless, it will never go to a trivial linear profile that you expect in diffusive systems. And I will talk about this profile a lot in this talk. So there is a divergent gradients at the contact here. And now this anomalous conduction is a result of modes of transport which are more than diffusive, which are super diffusive. And usually, for example, they can be related to ballistic sound modes, which exist in these systems. And they have to do with conserved quantities that decay slowly and they can propagate in a fast way. So that's the main reason why you have such anomalous heat conduction. Now, typical models that one study, one can think of the following thing. One can think of, for example, nonlinear coupled chain of linear coupled oscillators, like you have Hamiltonian in one dimension. You have some interparticle potential, nearest neighbor, which is a function of Qi minus Qi plus 1. And you have Hamiltonian like that. For example, like the Fermi pasta Ulam that people studied a lot, where the potential is some polynomial up to fourth order polynomial in the variable. Now note that if you take harmonic potential, it has to be nonlinear, because if you take harmonic potential, modes are uncoupled. It's basically, it does not equilibrate, the model does not equilibrate, and one gets some trivial result. For example, the current is going to be proportional to the temperature difference rather than to the difference divided by the system length. So it's a very high current because modes are not scattered by each other, and whatever you put energy from one side, it just propagates and goes to the other side without any obstacle. So one needs to take this nonlinearity into account. Another set of models is that of hard disks. For example, you can take hard disks, again in one dimension, and they are just colliding with each other, but you put them in some alternating mass. That is, you take a mass M1 and M2, and you put the particles you just arrange them as M1, M2, M1, M2, and then you let them evolve and couple them to a reservoir at the two ends. The reason you take these two masses different is because when the masses are equal, then basically, again, the system does not equilibrate, because each time they collide, they just exchange momenta. And therefore, they don't equilibrate. The momentum cannot equilibrate. And that's one way of making them equilibrate. Another set of models is that of stochastic models, where you put some stochasticity in the model. For example, you can think of hard disks with equal mass. So you have these hard disks, and they just move on the line. But in order to equilibrate them, you have to consider three-particle collisions. That is, every now and then you take, say, three particles which are sufficiently close to each other, and then you exchange their momenta. And you redistribute their momenta in such a way that you want to conserve the total momentum of the three particles and the total energy. Okay? You can do that, and you get new momenta satisfying. Now you have two conditions and three variables. And the way this is done is by basically, you see, this is a sphere in 3 dimensions, and this is a plane. And when you take the intersection of the sphere and the plane, you get a circle. And you choose, on the circle, you choose a point at random, and after a collision. So this is a stochastic way of redistributing the momenta and equilibrating the system. So that's another model that one can think of. Now, there are two broad approaches, classes of approach in studying these systems. One is a non-equilibrium setting. That is, you take a system, one of these models, for example, you put a temperature difference on both ends and study the steady state. And from the steady state, in principle, you can get the current and whatever. This is very difficult because, and there are very few models for which this can be done, because it's a non-equilibrium steady state, and there's no general formulation for which this can be done. The more common way of studying these systems is to look at equilibrium settings. That is, to use linear response theory and to apply Green-Kubo formula to calculate the conductivity. That is, you make a very small change. You look at change of temperature on both ends. You look at the response of that, and the response you can express as an equilibrium correlation of the appropriate currents. So, for example, the heat conductivity can be written as the JJ correlation. J is the instantaneous current correlation function at different points, different times. You have to integrate over the x and y and over t, and then you normalize. And basically, this gives you the heat conductivity of the system, while this average is calculated in equilibrium. Okay, so you make that's just linear response theory, and this is equilibrium calculations, which in principle you can sometimes perform. So basically, if you just take the integral over x, this is of j of x is just the total current that we defined before, and the integral over y of this is the other total current in the total current here at time t equals 0. So basically, the kappa, the heat conductivity, is just the integral over time of the total current correlation function at different times. And this sometimes can be calculated, and from that one can extract the conductivity. Now, typically for these systems, as I said before, the total current correlation function decays at large times as 1 over t to some power, which is smaller than 1, which means that if you want to calculate the heat conduction, you take the integral of that. The integral diverges because the power law it decays sufficiently slowly, so that in these systems the heat conductivity diverges if you just strictly speaking calculate it this way. The way to apply this is applied for infinite system, basically. The way usually one applies to finite systems is to say, well, this total current correlation function cannot really persist if you have a finite system of size n, it cannot persist beyond some time, because if you have a perturbation of energy and it starts flowing towards the end of the system, then after some time, which is the system size divided by c, c is characteristic sound velocity, it reaches the end and then it leaves the system. So beyond that time, there should be no correlation. So what people do, just calculate the kappa, the heat conduction, integrate up to time, rather to infinity, up to time which is n over c, is this velocity. And that gives that kappa goes like n to the power delta. Okay, so it gives the relation between the heat conductivity and the system size. And it goes like n to the delta. And basically, the n to the delta turns out to be, the delta turns out to be the same alpha that we talked before, that the heat conduction, the heat conductivity diverges with the system size like n to the power alpha. So this is the alpha that has to do with the heat conductivity. So this the slow decrease of this correlation function is simply related to the divergence of the heat conductivity at finite system. Okay. Okay. How does one calculate, in principle, temperature profile? If one applies the linear response theory to finite systems, one gets a relation that the current at the point x is related to some kernel, kn of xy, times dt dy dy. That is, it's related, it's not a local relation like in diffusive systems where it goes like the kernel is not a local kernel. It turns out that the kernel is spread out, and as a result, you have to, it's related to the temperature gradient everywhere in the system through the kernel that you can calculate. And this kernel is basically the JJ correlation function, which you can calculate in equilibrium. The point is that this JJ correlation function has to be calculated at a finite system, n, and one has to take into account the coupling to the heat bath when you calculate that. And it turns out that this could be very different. You get different results depending on the coupling to the heat bath. And so one has to be really careful when one applies this mechanism. You cannot just cut the system at some size and things like that. You have to be very careful in calculating this. Okay, so basically that's okay. So let's see. So how do you use that to calculate, for example, temperature profiles? You see the following. First of all, you see that if this k, if the integral of this k, sorry, what am I doing? Yeah, here. If this integral of k, it diverges with n, it means that clearly the temperature profile cannot be linear, because if it's linear, dt dy is just a constant, and the temperature sorry. I'm going in the wrong direction. Yeah. Okay. Yeah. So this integral has to diverge. For example, if you take k of xy, just suppose it goes like a power law of x minus y for x minus y at large x minus y, then j, the current, would be, you have to, is just proportional to this integral of the kernel times dt dy. In principle, you can, okay, or if you just rescale everything with n, you say j of u is just x over n and y over n. You have to invert this, integral equation to find dt dv as a function, due to this existence of this kernel. And the point is that j is just a constant, right? Because you have a one-dimensional system. In steady state, it's a constant. And inverting this should give you dt dv. This can be done for this particular kernel. And it turns out that dt dv is just v times 1 minus v to the power minus alpha over 2. Alpha is the exponent of the anomalous heat conductivity. Okay? Which means that the temperature gradient at the two ends diverges, as I said before, and the divergence, it goes like with power law, which is alpha over 2. Right? Because dt dv near v equal to 0, it goes like v to the power minus alpha over 2. So this is a simplistic way of looking at things, assuming that the kernel is just a power law of the distance, because we know it has to the integral of it, which has to diverge in the when the system is large. This result, we know from explicit calculations that sometimes it's wrong, it does not apply, and therefore one has to look at it more carefully. And basically, that's what I want to do in this talk, discuss a specific model, look at how the coupling to the heat bath enters, how you calculate the temperature profile, and look at this singularity of the temperature profile at the ends when it couples to the bath. So what I would like to do is I will introduce a simple model. Bernard basically hinted to, he mentioned it at the end of his talk. So for this model, the current correlation function can be computed, finite system. use this to obtain the temperature profile. I will show you how the temperature profile can be obtained. Show that the meniscus exponents, meniscus exponent is this exponent nu that shows how the dt dx diverges at the boundary, that it varies continuously with the coupling to the bath. So the specific coupling to the bath, if you have some parameter there, it turns out that it's not a universal parameter. It has to do with the coupling to the bath. Unlike in most cases the alpha exponent, which is the exponent that determines the heat conductivity, the way the heat conductivity diverges. Then towards the end, I'll mention some relation to Levy flight picture that was introduced some time ago by some people, including Bernard and other people. And if I have time, and presumably I will not have time, talk about long-range correlations in normal heat conduction systems, so I may just say a few words about it. So here is the model I want to discuss. Okay, it's a harmonic chain with momentum exchange. That is, you start with a harmonic one-dimensional harmonic lattice where these variables are coupled by some harmonic potential, and they therefore obey the dynamics. Is just the usual dynamics that comes with this potential. But as I said, if you just have harmonic potential, it will not equilibrate and things will not work out. So in order to equilibrate it, in addition to the harmonic potential, to these dynamical equations, we introduce a stochastic momentum exchange mechanism. That is, every now and then you take a pair of nearest neighbor sites, and their momentum, you just exchange their momenta. So this stochastic move does not, it conserves momentum, it conserves energy, so it doesn't violate any thing, but it mixes the modes of the harmonic chain, and it allows the system to equilibrate. So that's the model. It's very simple. It's linear model, but it's and it was introduced some time ago, studied very extensively by people like Monasterio, Lepri, and many other people. I mentioned them earlier. Okay. Now you have to look at the coupling to the bath. So at site 1 and n, you look at, it's a free chain, so there's nothing beyond it. So the potential just gives you this omega squared q2 minus q1, the coupling to site number 2. But in addition, one adds the coupling to the bath, which comes through a dissipation term, which is coupled to the momentum. It's like a dissipation plus noise term. Okay, so basically you want this to thermalize with some temperature T, and these couplings, the coupling lambda and the noise xi, are related so that the noise, say xi1 at site 1, is just a Gaussian noise with zero mean, and the variance, which is 2 lambda T plus. T plus is the temperature of of the bath at the plus end, and T minus is the temperature at the minus end. So basically, the temperature is introduced with some noise term here with dissipation, which obey the fluctuation dissipation theorem with temperature T plus, and that's basically that's how it's coupled to the bath. Okay. Now you see that there is a parameter here, lambda, which basically controls the dynamics of the coupling to the bath. It does not change with the temperature, so there is a free parameter tells you how fast the system collapses with the bath. And what I want to show you is that the temperature profile and other properties would depend on this parameter lambda, although the temperature of the bath is the same no matter what lambda is. Okay, so Okay, so I want to get a little bit into this model. The way to do it is to look at the variable SI, which is just the difference between the Q's, the variable of the two sides. And in terms of these SIs, just the SI dt is written this way. The PIs are in terms of the S's. And the equations for the two boundary variables, P1 and Pn, are just written in this way. Again, the noise, the Gaussian noise, plus the dissipation term, viscosity. Okay. Okay. Now, we want to try to analyze this model. We would like to go into the hydrodynamic limit, into thermodynamic limit. So we want to look at the bulk equations in the hydrodynamic limit. Now, in the hydrodynamic limit, you see this model has three conserved variables. It's the density, the momentum, and the energy, right? We conserved all these three variables, as usual, which are basically SI. SI is basically the distance between these nearest neighbor particles, but SI is just 1 over the density. So that's what SI is basically can look at as the density, the PI, the momentum, and the energy, which is the kinetic energy plus the potential energy of each particle. So if you look at the equations for these three variables, the S, the P, and the energy, these are I just wrote them down, and from these two you can deduce the energy for the E, and go to continuum limit. See that the equations are ds dt is just dp dx, the dp dt is just ds dx, and the equation for the energy, basically the linear term in S and P vanishes, and it's basically a second order term. It's just d of ps dx. So that's the energy in the hydrodynamic limit. So the way to proceed is to look at, to diagonalize. Yes? No, this is just, yeah, of course. There is gamma. The gamma is the thing that allows you to mix and equilibrate. It does not change in the, in the hydrodynamic limit. It does not change. If you look at the local momentum of a region and you exchange momenta between them, it will not change that. It will provide. You see, you go from hydrodynamic to fluctuating hydrodynamics, and it provides the fluctuating term into that. Okay, I'll get to that in a minute. But this is, let's look at it as just dynamics that come from the Hamiltonian, from the interaction. So you have three modes, but they are coupled, right? This ds dt is coupled to the p, and the p is coupled to the s, and e is coupled to both. So you want to diagonalize them. So you define the three eigenmodes, or three normal modes of this system. There are phi plus, phi minus, and phi 0. And phi plus is basically omega s minus p, omega s plus p, and the energy is the third term. And so phi plus is just omega s. So these are the three modes, normal modes of the system. And you can write down the hydrodynamic equations in terms of these normal modes. And these are in terms of the S and P. In terms of the normal modes, it's just d phi plus minus d dt is just omega times phi plus or minus. So basically, this is the sound modes. These are the two sound modes which are propagating either to the right or to the left. And there is an energy mode which is just driven by the phi plus and phi minus, and it's written in this way. So this is the linear term is 0 basically. So it's only coupled to them through the nonlinear term in the phi's, and basically these are the three equations. Okay. Now you want to, as Bernard was asking, how about the momentum exchange things? This will introduce what's called, fluctuating hydrodynamics. That is, you want to look at the fluctuations around this mode, and this will introduce diffusion term in addition to the linear term, which provides the sound velocity, and a noise term, and basically and similarly for the energy mode, and basically these are the equations that you are interested in solving, in looking into. So the etas here are uncorrelated noise, Gaussian white noise, and basically the stochastic momentum exchange, basically it's the mechanism that provides for this diffusion and for the, okay. So these are the equations of propagation of this mode, of this system in the hydrodynamic limit. Now note here that if you look at the current of the, if you just average the current of the energy current, it has to do with phi plus squared minus phi minus squared. So basically, if you solve the equations for phi plus phi minus, you can calculate the current of the energy current, which comes from here, and see how it looks. So this is basically the current, instantaneous energy current in the system, which you want to calculate. So you want to solve the equations for the two modes, phi plus and phi minus, which are the sound modes that propagate in the system. Okay, so to do that, you have to consider, to be careful with the boundary conditions. So the question is, how do you start with microscopic equation, you go to the hydrodynamic equations, and you want to write down the boundary condition for the hydrodynamic equations, which is usually not a simple thing to do. So the way one can do it here is the following. Look at the equations for this. These are the equations for dSi dt and the dpi dt that we wrote before. We need only these two equations. And then this is the equation for site number 1, which is different, right? In the microscopic mode, it's coupled, P1 coupled only to S1. There is no S0. There is no, like there should be here. And it's coupled to the bath. If you just forget the noise for a minute, it couples to the dissipative term in the bath, okay? Now you want to regularize this, that is, you want to bring this equation to the same form as this one. So the way to do that is to add a variable S0, right, to the left of it. And you write dp1 dt is just omega squared S1 minus S0 to bring it to the same form. But then you have to add it, and you have this other term. So to bring this equation to the same form as this equation, you have to demand S0 should satisfy this equation. So you added variable to the left, and you demand that it satisfies that. It has to satisfy at any time. So therefore, you also want the derivative of this with time to be satisfied. You take the derivative of this, dp1 dt is just, you write it this way. And the S0 dt, you assume that it satisfies a similar equation like everybody else, and you get this is the other equation. So these are the two equations that should be satisfied at the boundary. And then you write them, you take these two equations, and you write them in terms of the normal modes. So these are the two equations that we had before. Express S and P in terms of phi plus and phi minus, the two. And when you do that, you see that these two equations are written that phi plus minus r phi minus at x equal to 0 at one end is 0, and the derivatives should also satisfy similar equation at one end, and similarly at the other end. So these are the boundary conditions that the hydrodynamic equations should satisfy for this model. Now this r, if you just put it here, it's a function of lambda and omega. R is just lambda minus omega divided by lambda plus omega. Okay? Now what is this r? R is just a reflection coefficient. It means, this is the equation that you have for phi plus and phi minus. It means that phi plus or phi minus at x equal to 0 should be r. What is this? Phi minus is a sound wave propagating to the left towards 0. It is reflected at the boundary and becomes a phi plus. But the amplitude of phi plus divided by phi minus is just r. So it is reduced by a factor of r. So it means that every time a sound peak hit the boundary, it is reflected with a reflection coefficient r. Okay? Basically, that's the meaning of this boundary condition. And r is related to the force constant that defines the harmonic potential, but it's also related to lambda. Lambda is the coupling to the bus. That's the main issue. Okay, so let's see how it works. This is just a result of a simulation. You start here some early time with some, just give the system a kick in the middle. So you see, so for example, you plot the momentum kick at the middle. You want the momentum distribution. What is, you generate this energy mode, the diffusive mode, and you also generate the other two modes, the sound propagating to the right and the sound propagating to the left. And these are the two modes that started propagating. This is after some time, t equals 200. What happens when they, after later time, they reach the boundary, and what you see is that the phi plus mode, the one moving to the right, is reflected, and it starts generated phi minus going to the left. Similarly, on the other hand, and after some time, you see that it just disappeared, and the whole. So there is a reflection, and the reflection, and if you measure the amplitude of this reflected mode divided by the amplitude of the mode that hits the system is just this r that I was talking about. So this is a result of simulation. You can measure and you see that it's indeed, that's what happens in this model. Okay. Now, just a comment about this r. It is, as I said here, when lambda is equal to omega, r is equal to 0. It means that you are at some resonance. That is, the dissipative term that you put at the end with coupling to the reservoir is equal to the normal frequency of the oscillators that you have in the system. In that case, r is 0 and there is no reflection. So basically, if you have a sound wave, it reaches the end and then just leaves. On the other hand, when lambda goes to infinity, r is equal to 1. So basically, this is like fixed boundary conditions. So you close the system, you don't let it basically move. So this is like closed system. Also note that r can be negative. Negative r means that you flip the amplitude of the mode that enters. That is, you see here, for example, here r is negative in this simulation. R is minus 0.6, which means that the negative amplitude becomes a positive amplitude coming on the other side. So, okay. 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 So now now we have all the tools to really look into the modes of the system. Let's look at the equation for phi plus minus. Okay, so these are the equations that we want to solve. So these are basically linear equations. You know, you can solve them. There is the green function of, and forget now the boundary terms. Let's suppose r is equal to 0, so there is no reflection from the two ends. The Green's function of this diffusion equation, basically this is diffusion equation with the propagating term, is just f, x, y, and t is just Gaussian, right? X minus y minus sigma omega t. Sigma is plus or minus depending on whether it's a right-moving sound wave or left-moving sound waves, you know, depending on phi plus and phi minus. So basically, this is the perturbation moves with velocity omega. That's from this term. But because of these terms, the noise and the dissipation, it becomes a Gaussian, and it's just a propagating Gaussian. That's the Green's function. And the solution of this equation with the noise and the initial condition is just you integrate over this Green's function times the initial condition at time t equal to 0, right? That's the plus you have to apply it to the noise term at any given time. So this is basically that's the it's a linear equation. You just use that. So once you have the initial condition and the noise, you have the solution for phi. Now, in the case of nonlinear, of non-zero reflection, you have to take the reflection into account. And the f, the Green's function, you know, when it reaches the boundary, it is reflected as a Gaussian peak with a reflection coefficient r. So each time it is reflected, so if f plus hits the boundary, it's reflected as phi minus at the boundary, but with amplitude which is reduced by a factor of r. So basically, the Green's function can be written simply as the sum over all these reflected modes and their interchange from phi plus to phi minus, and they are reflected on both boundaries and multiplied by the reflection coefficient that you have here. Here, sigma and tau are plus or minus 1. So this is the Green's function of, say, you hit with a plus and you generate a minus at you know, you give a kick at x, you generate with sigma plus, you generate a y, a kick at y, later time t with tau. Okay, so basically you have to do that. And this is the Green's function, and basically the solution, therefore, in the general case is not just a simple Gaussian, but it's a sum of many, many Gaussian reflected and with appropriate sign. So this is the solution. It's the propagation of the initial condition and the propagation that comes from the noise term. So remember, in order to calculate the, let me just summarize what we had before. If you want to calculate the temperature profile, we know the current. This is the current, is just phi plus squared minus phi minus squared. This is the instantaneous current. In the steady state, we have to calculate, we know J in the steady state is just equal to the integral of this kernel times dt dy. And the kernel is the JJ correlation function. So basically, we have to calculate the JJ correlation function, which is phi plus squared minus phi minus squared as x and t, correlation function with phi plus squared at y at time t equal to 0 minus phi minus squared at y at time t equal to 0. So basically, it's a phi squared correlation function that we have to calculate in order to calculate this correlation function. Once we know this correlation function, we have the kernel. Once we have the kernel, we can invert it and calculate the temperature profile, knowing that J, the stationary state current, is just a constant. Okay? So we have the solution for the phis. We have to calculate the phi squared correlation function. That gives us the JJ correlation function, calculate the kernel. So basically, that's the scheme, which can be done because the kernel is known, the phis are known in terms of the Gaussian kernel that we showed before. So the result, the upshot of the story, it's basically calculating phi squared correlation functions. That gives you the current. And this is the result. So full result. So it looks like a horrible expression, but actually it's very simple. If you take, for example, this is the sum. U and V are just x over n, just rescaled x and y. R, capital R, is just R squared, is the reflection coefficient squared. So this is this. And basically, this has to do with the reflected, the correlations that come from the reflected waves that come back and forth from the two ends. If the correlation function is just 0, consider the case where lambda is equal to omega, it is 0, then the kernel is just given by 1 over square root of u minus v. That's the thing that I mentioned at the beginning, that the kernel goes like 1 over x minus y to some power, okay? But in fact, if there are some reflections, one has to take into account all these terms into account, and as we'll see, they could be, they would affect the temperature profile of the system. Okay. So let's first consider R is equal to 0 indeed, when lambda is equal to omega. Then in this case, the kernel is just equal to 1 over u minus v to square root. That's what we found for this model, right? Just this term. Then the current in the steady state is basically just square root of n. You know, after you do the rescaling, it just you have to calculate to invert. Okay, this is a constant. You have to invert this relationship, and this relationship gives you the dt dv is just, as I mentioned before, it's v times 1 minus v to the power minus alpha over 2, which in this case, since alpha is equal to a half, we get a divergence of the temperature gradient with an exponent 1/4. Alpha over 2 is a quarter, and you get the quarter that I mentioned before. But it applies only when the reflection coefficient is 0. So it's only in that case it is correct. Turns out that when the reflection coefficient is not 0, this is going to change the profile, not only the meniscus, but also the whole profile. And let me just discuss that a little bit. Okay. Now, this model for R is equal to 1, that is for fixed boundary conditions. So suppose you have a closed boundary condition, was analyzed in a very nice way by these people some time ago. And they found that the meniscus exponent is 1/2. That is, so you already observed that when the reflection coefficient is not 0, this result does not apply. It's already there. So clearly, it should depend. The profile and particularly the meniscus exponent, the way the temperature gradient diverges at the end, should depend on the reflection coefficient. But how does it depend on it? Okay. How do you calculate it? So let me just spend a couple of minutes to show you how you can get a simple relation between the reflection coefficient and the divergence of the temperature profile at the end. We have a relation like that. Take a derivative on both sides with respect to x. So this is the current at point x. This will give you 0, right? Because the current is constant. And this would give here that dk du, that's dk dx from here, and this should be 0. This is a principal value because one has to be careful. It's a principal value integral that you have to calculate. It's because the divergence, the dk du could diverge in a rather high power, and you have to be careful in doing that. Okay. So you want to do, so this is the relation. You have dk, this integral has to be equal to 0, where this is the kernel. Now, when you look at this integral, suppose that the dt dv is just v to the power minus nu, that indeed there is some singularity at the end. Then if you just insert it here and look at the resulting integral, you see that there is going to be a term which is u to the power minus nu minus a half when you integrate. But it has to be 0, and therefore the coefficient of this has to be 0. The coefficient of this term must be 0. Right? Let me show you how it comes. For example, if you take this term only first, you multiply it by, you assume that dt, and you look at whatever, this integral that comes only from this term. So you have to take, it's the integral you have to calculate is dk du, and therefore, if k is this, you have, the derivative gives you power 3/2. So you have to calculate this integral. That's because here it's an absolute value, so you have to separate it to v less than u or v larger than u, so you have to do that. You just calculate, you see how it goes near u goes to 0, and it goes with this power law that I mentioned before. Now, so clearly this has to cancel somewhere, and it turns out that it's going to be cancelled. The only other term in this whole sum that could contribute something like that is these two terms when n is equal to 1. That is only from the first reflection that you can get such a singularity, because when you have the first reflection, for example, when n is equal to 1, 2n minus 2 is 0, and there is a singularity of this integral when u plus v when they are close to 0. All the others are regular integrals, they contribute nothing. So when you calculate the similar terms that come from these two terms, just one reflection, you get this expression. And the expression is that this is the term that comes from the first term. This is r times, this is coming from these two terms times a different integral. This has to be 0. And that gives a relation between r, the reflection coefficient, and the critical exponent, the meniscus exponent nu. So that's the relation. And indeed, you see that it's a continuous function of between r and nu, and r is a function of the coupling to the bath. And this is the relation. It goes from, this is the expression that I just showed you, and the points are this, and the points are just a simulation of this model. And you see that it agrees very well, and it goes from 1/4 to 1/2, depending on whether it's 0, whether r is 0 or 1, and it's a continuously varying function. So one can actually calculate this very non-trivial temperature profile. This is the temperature profile for r equal to 0. This is for r is equal to 1/2. This is what's done here is you subtract the linear slope, and this basically has to go to near 0, and you see it's up. Sorry. this is for sufficiently small system. It's only n is equal to 100. In the thermodynamic limit, it should go flat. Okay. One other comment, one may consider different lambdas on the two reservoirs. You can think of a reservoir which is coupled very fast on lambda large dissipation term there, and a smaller one on the other side. It turns out that it doesn't really matter. Basically, the reflection coefficient becomes now R plus times R minus, and R plus minus are just the lambda plus minus over that. So it's a function of the product of the two, because it's just these waves going back and forth. They have to be reflected once from the right, once from the left, and they basically fill both reservoirs in this way. So you get the same result, except that you have that. Yeah, an interesting thing is when R plus is 0 and R minus is not, it's as if this effective R in the end is 0. It means that if it's half an infinite system, then that's enough. It's like, okay. Okay, let me, a few more minutes, and let me just mention, okay, so basically, that's what I wanted to say about this model, that we can actually calculate the temperature profiles. You can apply this Green-Kubo function formalism, provided you take into account the coupling to the reservoir. And the coupling to the reservoir is important when you want to deal with finite systems. Now, a few years ago, a group of people, including Lepri, Politi at some point, and then Dar, Saito, and Bernard, looked at a Levy-Flight picture of the heat transport in these systems. And it's a very simple model, and which says the following. Suppose you have particles that hop on a line with hopping rate from y to x, at least for large x minus y, they hop with some rate which goes like x minus y to some power. Okay, and so it's a Levy-Flight. Beta is between 1 and 2, so that the average distance is finite, but the variance diverges, and that's what makes it Levy-Flight, basically, a not usual diffusion. So there is some probability of just making a large hops to the end. Now, then you couple it to a bath. That is, you take a left bath with a density for x less than 0 to be density to be q plus, and for the right bath, x larger than L is q minus. So you couple it particles which are hopping, they are non-interacting and they are hopping, and there is a constant density here, and you ask what is the density profile in between when you consider this thing. Now it turns out that this work was mainly, the first one was mainly numerical, and the work here of Dar, Saito, and Derrida was analytic for the case of our reflection coefficient equal to 0. Sorry, what am I doing? Okay, good. So it turns out that for this model, one finds that the current is, again, related, the particle current is related to some kernel times the gradient of the density. Q prime is the gradient of the density. And this kernel is related to the hopping rate that I described here to this hopping rate by this relation that the second derivative of the kernel is this hopping rate. Now, you can generalize the model and take some reflection coefficient. That is, whenever a particle hits the boundary, it is reflected and continues the walk into the flight, into the system in a reflected way, and it hits the target within the system after a reflection with reflection coefficient r. So that if you take W of xy to be the same form that we discussed before, then we should get the result for the Levy flight density profile with a reflection coefficient. Here, the power law is 5/2 rather than 1/2. It's because the W, the hopping rate, is the second derivative with respect to k. So basically that. And from which you can get the meniscus exponent. It was conjectured from the numerical simulations of Lepri, Politi, and Politi. They conjectured that the meniscus exponent should be related to the reflection coefficient in this way. It's a linear relation. Beta, the exponent beta, is related to the alpha exponent of the heat conductivity. So basically, for alpha is equal to 1/2, the relation should be that. Well, it's very close to that, but it's a little bit different. The relation is a little bit more complicated if you take into account the real kernel that has to do with the reflection coefficient. Okay. So this was just a comment on this Levy flight model. And here you see that the Levy flight is provided by this sound in this heat conduction problem, is like by the sound modes that are propagating in the system and hitting the boundaries and are reflected from the, okay. So let me just summarize now. We used hydrodynamic, fluctuating hydrodynamic approach to calculate temperature profiles of these heat conducting systems. Here we used it for this specific model of harmonic chain with momentum exchange, and one can calculate profile itself, but also, in particular, the meniscus exponents, and to show that it is a function of the coupling to the heat bath. There is a close connection to Levy flight picture, and the application to other models, one has to explore it and to see how general it is, this kind of thing. Okay, with that. Thank you.